Hey everybody, Dr. A here, and in this video we're going to be exploring an example of computing a centroid using the integral formulation. But before we get started, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's dive into it.
In this example, we're being asked to compute the coordinates of the centroid of the curve, and we're given this plot here. So the curve we're interested in is this segment right here, okay? And this curve is governed by the equation y equals x cubed. And we see that we're also bound by x equals 1 and y equals 1. So again, we're being asked to compute the centroid of the curve, not an area, okay? This is not an area centroid. This is a curve centroid. And our coordinates are going to have coordinates of length. So we have x and y in inches, all right? So under the solution, I've already written out the first part of this. To note, this is a two-dimensional problem, and we can easily see that by the given information. We are given a curve in a 2D set of axes, x, y axes, okay? Now, in a real-life application, what is this pretty similar to? Well, it's a curve, so maybe it's perhaps a bent wire or a pipe of some sort. Maybe it's something that is got a much longer length than it does cross-section area, so it's modeled as a curved segment, okay? And so what we're being asked to compute is the centroid x bar comma y bar. So if you look back in your notes, and from the previous video, how do we formulate the coordinates of the centroid of a curved segment, right? Well, in your notes, you have centroids, and you have lines and curves, and then areas, and then volumes. So this is the line/curves category. So if we look at this, we have x bar and y bar. I forgot my tildes here, but we got x bar equals integral x tilde dl divided by integral dl, and then something similar for y bar, but we have a y tilde there. And we need to remember that, and we mentioned this before, x tilde and y tilde represent moment arms. Okay, we're going to see kind of how these get pieced together as we move through this problem. So let's tackle this. Let's figure out how to piece all this together. I mean, we have these nice general integral forms here, right? But we have really nothing specific in these integrals yet. So let's dive in and take a look at it. So I'm going to redraw my curve here just so I can make some further sketches on it. Here's x in inches. Here's y in inches. Here we go. Oop. This is 1. This is 1 right here. And then the equation, of course, was y equals x cubed. Okay, so again, if we're looking at a curve piece, what we're really interested in is a differential length. That's why we have these DLs here. We're interested in a differential length. So what we're going to do is somewhere on this curve, we're going to zoom in here and we're going to look at a teeny tiny differential linear segment. Okay, so I'm going to draw this out to the right here, much bigger. So this right here, this linear segment, it's going to have a length of DL. So right here, this is DL right here, okay? Now, when you zoom in on a little differential piece of a curve, you can treat it as a line, okay? It's so infinitesimally small, you can treat it as a teeny tiny line segment with length DL. Now, if we're treating this as a teeny tiny line segment, guess what? It's going to have a horizontal component as well as a vertical component. So that teeny tiny line segment is going to make a little right triangle. And we can call the horizontal piece of this dx, and we can call the vertical piece of this dy, okay? And so on our original figure, we've got dx right here and dy right here. All right, so what do we see here? Well, if it's a right triangle, we can relate these sides using the Pythagorean theorem. So we can say DL equals the square root of dx squared plus dy squared. All we're doing is we're applying the Pythagorean theorem to this differential triangle, this teeny tiny triangle. Even though it's a teeny tiny differential triangle, it's still a right triangle. So Pythagorean theorem still governs, okay? Now you may be thinking, okay, this is nice, but what do we do next? I still don't know anything specific. Well, let's think about it. We know the equation of this curve, don't we? It's y equals x cubed. That was given to us, okay? So if we know what y equals, can we say dy dx equals 3x squared? Yeah, absolutely. All we did was we just take the first derivative of the equation of this curve, and what do we get? We get something in terms of differentials, dy and dx. And sure enough, we have this dx squared and dy squared built into that Pythagorean relationship. So now watch what I can do. I can separate these differential variables, and I can say dy equals 3x squared dx. So remember, a derivative works kind of like a fraction. This denominator gets multiplied up here, and we can break this up into two parts. We sometimes call this separation of variables, okay? So what do we see now? Well, check it out. I have now an expression for dy then I could substitute into this Pythagorean identity. So now what can I do? I can say dl equals square root dx squared, and now I can substitute this differential in for dy, okay? And so I'm going to have a quantity 3x squared dx squared, okay? Just like that, all right? Oh, don't forget your plus sign right in between, all right? So now let's kind of work this out a little bit more. We have dx squared, and we're going to say plus 9x to the fourth dx squared. So all I did was I squared all of the terms inside of this parentheses here, all right? Now I'm going to do a little bit of algebra. Hopefully, it's not too complicated, but notice that I have like terms inside of this radical. I have a dx squared as like terms in each of the terms in the radical, all right? So watch what I can do now. I can say dl equals square root of the quantity 1 plus 9x to the fourth, and then dx squared outside of the parentheses, but still under the square root for now. So all I did was I factored out this dx squared from each of these terms, and now I have the quantity 1 plus 9x to the fourth times dx squared. Now I can use some properties of radicals, and I can say this is 1 plus 9x to the fourth square root times the square root of dx squared. And of course, we should be able to just hopefully look at this and see that, let me draw that a little better, see that we're left with 1 plus 9x to the fourth dx, because we took the square root of dx squared, all right? So check out what we have now. We have a term for dl, all right? Now that term for dl, guess where that's going to go? That's going to go into our integrals for both x bar and y bar, okay? So now we can rewrite the integrals. We can say our integrals become, and we're going to have x bar equals integral x tilde, and then dl is square root of 1 plus 9x to the fourth dx, and then the denominator is integral 1 plus 9x to the fourth dx, and then similarly y bar is going to be integral y tilde 1 plus 9x to the fourth dx divided by integral square root 1 plus 9x to the fourth dx. Okay, so now we're getting somewhere. But the next couple things we need to worry about are these tildes, right? This x tilde and y tilde, okay? So remember, we've tried to emphasize now, x tilde and y tilde represent moment arms, okay? Moment arms. So let's start with x tilde first. How do we figure out what x tilde is? Well, let's look at our redrawn figure here, okay? And we have to remember what this means, okay? We have to remember what this means. I'm going to use green. We have to remember what this means. So x tilde represents a moment arm from where to where. Think back to our mathematical framework. X tilde represents a moment arm from the y-axis to the curve, okay? So this is x tilde, okay? So again, x tilde represents some kind of arbitrary moment arm from the y-axis to the curve. You can look at it here. You can look at it where I drew it in green, maybe even all the way up here, right? X tilde is a symbolic representation of a moment arm from the y-axis to the curve, okay? Think back to our mathematical formulation from a previous video, all right? So in this particular case, when we're regarding x bar, what is x tilde going to be equal to? Well, it's just going to be simply the x coordinate itself that we're interested in to the curve. So we're going to say x tilde equals x here. Okay, again, want to emphasize x tilde is the symbol for a general moment arm, but for this particular piece of the problem, if it's always measured from the y-axis to a point on the curve, then x tilde is the x coordinate. It is an arbitrary x value, okay? So in that case, we're going to say that x tilde becomes just x, okay? So then I can rewrite this as x bar equals integral x square root 1 plus 9 x to the 4th dx, all divided by integral square root 1 plus 9x to the 4th dx, okay? Now, the next thing we need to think about is these need to be definite integrals. You don't want a plus c constant. You need a definite integral. So if you're taking a definite integral, look at our figure. Where are we going from? We're going from 0 to x equals 1. So if you are taking an integral with respect to the variable x, then we need to go from 0 to 1 inch as these definite integrals, okay? Now we're done. We're ready to evaluate this. Now I'll go ahead and tell you this is a tough one to do by hand, so I'm going to use the TI-36X Pro to evaluate these two integrals. And please, 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 you have to understand you cannot cancel things inside these integrals, okay? You're taking the integral of a function, essentially. You can't just say, oh, cancel this square root with this square root because they're the same. They're not the same because they're inside an integral operation, okay? So let's evaluate this numerator first. 0 to 1, x times 1 plus 9x raised to the 4th power, and then we need to square root that. And I get 0.942. My units will actually be inches squared in that numerator. And then the denominator integral, we're going to evaluate this denominator. And I'm doing this integral again in my calculator. 1 plus 9x raised to the 4th, and then raise that to the 0.5 power. That's the square root. And that denominator will give me a value of 1.548 inches. And I get a value of 0.609 inches, okay, as x bar. That's one of my answers. That's half my answer right there. What about y bar? What about y bar? So we're going to do the same kind of thing, but we need to figure out what is this y tilde here? What does that mean? So looking back at our figure, remember when you're calculating y bar, you're looking for y tilde, which again is a type of moment arm. And what is y tilde? Well, y tilde is a measurement from the x-axis up to the curve itself. This is y tilde. So y tilde could be this, could represent this little moment arm, this moment arm, this moment arm, all the way up to this moment arm. Either way, it's a distance from the horizontal x-axis up to the curve itself. Well, y tilde is the general symbol, but for this particular problem, what is y tilde? Well, all it is just the function. It's just y, right? What's the distance from the x-axis up to the curve? Well, it's just the function itself. It's the curve itself. So that's going to equal y, which equals x cubed, okay? So I'm going to make a note down here. I'm going to say y tilde equals the function y, which is just my function x cubed, okay? And then I can substitute this value into y tilde here, all right? So let's work that out. We're going to say y bar equals integral x cubed 1 plus 9x to the fourth dx. The denominator is the same, right? Integral square root 1 plus 9x to the fourth dx. You're still integrating with respect to the x variable, and our problem goes from 0 to 1 inch. So we're going to type that in, write that out, 0 to 1 inch as my definite integral. And then we're going to calculate y bar here. And the denominator is identical to my x bar calculation. So that's 1.548 inches. If you notice, these denominators are the same, okay? It's the numerator that's different. So we need to type in this numerator integral into a calculator. Don't try to be a hero and do this by hand. You can do this in your calculator. This is not really meant to be a mathematical exercise. It's really meant to use math as a tool to solve this particular problem. 1 plus 9x raised to the fourth, and then raise that to the 0.5. So my calculator gives me a value of, for the numerator, 0.567 inches squared. And when I divide these numbers out, I get 0.366 inches. So my coordinates of the centroid are x bar comma y bar equals 0.609 inches, comma 0.366 inches. And that's my answer. And if you wanted to include that in on your plot up here, then that would be, let's see, 0.609 and 0.366. So that's going to be maybe right here, and yeah, it's hard to see that. It's somewhere in this general area, okay? Somewhere in this general area. So you could draw that to scale and find out exactly where that is. In fact, I am a little curious as to where that is. So while the video is still rolling, I'm going to say 0.609 cubed. Yeah, so actually the it's actually above the curve just a bit. So if this is 0.609, it's actually up here somewhere. So this right here is our centroid. This is obviously not drawn to scale. In fact, I could probably draw it even better than this if I really wanted to. 0.609 is actually more about right here, 609. And so right there is our centroid, 0.366. How do I know it's about right here? Well, what I did was I plugged in 0.609 into x cubed just to see what the function value was there, and it was 0.23, and then the y coordinate of the centroid is higher than that, so it's 0.36, so the y coordinate of the centroid is a little bit above the curve. That's how I'm able to tell where that is. So that's it. So be very careful. Look at the examples in the book. There's some good examples in the book that are similar to this to give you some variety.